Imagine a place in the cosmos where the very fabric of reality is torn apart, where time stops dead in its tracks, and from which nothing, not even light, can ever escape. These are black holes. They are the ultimate abysses, invisible titans scattered across the universe, warping space and driving massive stars into catastrophic gravitational collapse. For decades, they were thought to be mere mathematical ghosts, but today we know they are real, terrifyingly powerful, and actively shaping the destiny of everything we see. Today we are going to explore the mystery of black holes, diving deep into the darkness to uncover how these cosmic monsters work, how they shatter the laws of physics, and what truly happens if you fall inside. It is a journey to the absolute edge of existence. If you are ready to venture into the deepest unknowns of the universe, please take a moment to like this video and subscribe to the channel to support our scientific journeys. We love building this community of curious minds, so please leave a comment right below letting us know exactly where in the world you are watching from and what time it is for you right now. Whether it is late at night in New York, a quiet afternoon in London, or early morning anywhere else on Earth, we want to read your stories. Now, brace yourselves as we cross the event horizon and begin our countdown into the terrifying, mesmerizing science of the cosmic abyss. Long before modern telescopes scanned the deep cosmos, the darkest concept in physics began as a radical whisper in the 18th century. The foundational thinking did not start with Albert Einstein, but with the gravitational framework established by Sir Isaac Newton. Newton described gravity as an attractive force acting between masses across space, governed by an inverse square law. Under Newtonian physics, every object possessing mass requires a specific speed to escape its gravitational pull entirely. This boundary is known as the escape velocity. For Earth, the escape velocity is roughly 11 kilometers per second. For the Sun, which is far more massive, it rises to over 600 kilometers per second. The math implies a straightforward rule. If you increase the mass of an object or compress its radius, its escape velocity skyrockets. In the year 1783, a visionary British clergyman and natural philosopher named John Michell sat down with these Newtonian calculations and asked a terrifying question. What would happen if a star became so incredibly massive, or was compressed into such a minuscule volume, that its escape velocity exceeded the speed of light? Michell knew that light travelled at a finite speed, which had been calculated roughly by Ole Romer a century prior. He reasoned that if a star's gravitational grip required an escape velocity faster than light itself, all luminosity emitted by the star would be pulled right back down to its surface. The star would become entirely invisible to the outside world. Michell called these hypothetical entities dark stars. He even wrote a letter to the Royal Society of London detailing how astronomers might detect them. By looking for visible companion stars that seemed to be dancing around an invisible, massive partner. A decade later, in 1796, the French mathematician and astronomer Pierre-Simon Laplace independently arrived at the exact same conclusion in his treatise on celestial mechanics. Laplace noted that the gravitational pull of a sufficiently large body in the universe could be so immense that no light rays could ever break free from it. However, during the 19th century, the dark star hypothesis fell out of favour. Physicists began to embrace the wave theory of light, which suggested that light was a massless wave travelling through an ethereal medium. If light had no mass, scientists assumed, it could not be influenced by Newtonian gravity, which relied on the mutual attraction between physical masses. The brilliant concept of an invisible cosmic trap was shelved, treated as a mathematical curiosity that did not conform to the accepted laws of nature. The true intellectual revolution arrived in November of 1915, when Albert Einstein presented his groundbreaking theory of general relativity to the Prussian Academy of Sciences. Einstein completely overturned the Newtonian view of the cosmos. He declared that gravity is not a mysterious force acting at a distance. Instead, gravity is a structural manifestation of geometry. Space and time are welded together into a four-dimensional fabric known as space-time. Massive objects like planets, stars, and galaxies do not pull on things directly. Rather, they warp, bend, and curve the fabric of space-time around them. Think of a heavy bowling ball resting on a flexible trampoline. The ball creates a deep depression. If you roll a small marble across the trampoline, it will curve toward the bowling ball, not because of an invisible tugging force, but because it is simply following the contours of the curved surface. In the universe, matter tells space-time how to curve, and space-time tells matter how to move. Light itself, despite having no rest mass, must travel along these curved geometric pathways. Just weeks after Einstein published his field equations, a German physicist and astronomer named Karl Schwarzschild achieved something remarkable. While serving on the Russian front during World War I, enduring harsh military conditions and suffering from a painful autoimmune disease, Schwarzschild found the very first exact mathematical solution to Einstein's notoriously complex equations of general relativity. He sent his findings in a letter to Einstein, who was deeply astounded by the elegance of the math. Schwarzschild's solution described the geometry of spacetime around a perfectly spherical, non-rotating mass. But buried deep within his beautiful equations lay a dark, unsettling secret. The mathematics revealed that if any amount of mass is compressed down below a specific critical radius, the curvature of spacetime becomes infinite. This critical boundary would later be immortalized as the Schwarzschild radius. If you were to compress the entire mass of our Sun into a sphere with a radius of just 3 kilometers, or roughly 2 miles, it would cross this threshold. If you compress the entire Earth down to the size of a small marble, roughly 9 millimeters in radius, it would do the same. Within the Schwarzschild radius, the equations showed that spacetime becomes so severely distorted that all possible paths for matter and light turn inward. The coordinate system itself flips. Outside the boundary, you can move forward or backward in space, but you can only move forward in time. Inside this critical radius, the direction toward the center becomes a direction in time, not space. Just as you cannot stop yourself from moving forward into tomorrow, an object inside this radius cannot stop itself from falling toward the absolute center. Despite the mathematical perfection of Schwarzschild's work, the scientific community, including Einstein himself, flatly rejected the idea that such objects could actually exist in the physical universe. Einstein believed that nature would always find a way to prevent such an absurd state of affairs. He wrote papers arguing that the angular momentum of collapsing particles would prevent them from shrinking past this critical point. The general consensus for decades was that the Schwarzschild radius was an idealistic mathematical artifact, a division by zero that could never happen in the messy, real world of astrophysics. The skepticism began to crack in 1939. An American physicist named Robert Oppenheimer, working alongside his student Hartland Snyder, published a revolutionary paper titled On Continued Gravitational Contraction. They utilized general relativity to model what happens when a massive star completely runs out of its nuclear fuel. Without the outward thermal pressure generated by nuclear fusion, the star's immense gravity wins the internal tug of war. Oppenheimer and Snyder demonstrated that if the dying star is massive enough, absolutely no known force in physics can halt its inward collapse. The star will continue to shrink indefinitely, pulling its entire mass past the Schwarzschild radius. To an outside observer, the star would appear to dim and freeze in time right at the boundary due to extreme gravitational time dilation. But from the perspective of the collapsing matter itself, it would pass straight through the boundary in a finite amount of time, collapsing down to an infinitely dense point. World War II broke out immediately after the publication of Oppenheimer's paper, diverting the focus of the world's top physicists toward nuclear weapons research, and the study of gravitational collapse languished once more. It was not until the 1960s that interest was reborn, sparking what historians call the golden age of general relativity. John Archibald Wheeler, a brilliant American theoretical physicist, popularized the evocative term black hole to describe these objects, instantly capturing the public imagination and replacing dry terms like frozen stars or collapsed singularities. Concurrently, mathematicians like Roy Kerr advanced the field by solving Einstein's equations for a rotating mass, providing a far more realistic model for actual stars in the universe. Theoretical physicists like Roger Penrose introduced new topological methods, proving via singularity theorems that black holes were not just mathematical anomalies caused by perfect spherical symmetry. Penrose proved that if an event horizon forms, a singularity is an inevitable, physical consequence of general relativity. The journey from Michel's invisible dark stars to a rigorous geometric understanding of collapsed spacetime was complete. The black hole was no longer a ghost haunting the equations. It was an inevitable cosmic reality, waiting to be discovered in the deep, dark spaces of our universe. To truly understand a black hole, we must strip away our everyday perceptions of physical objects. A black hole is not a solid sphere of dark matter floating in space, nor is it a hollow drain or a cosmic tunnel. It is a highly structured distortion in the geometry of spacetime itself. If we could dissect one of these invisible titans, we would find a series of distinct, nested architectural zones, each governed by increasingly extreme laws of physics. The anatomy of a black hole is a masterclass in cosmic extremes, stretching from the hyper-vibrant rings of glowing matter millions of miles away to an infinitely crushed point at the absolute centre, where space and time cease to exist. The outermost boundary of a black hole's immediate influence is the accretion disk. This is the monster's cosmic feeding trough. Because matter rarely falls directly into a black hole in a perfectly straight line, gas, dust, and torn-apart stars swirl around it instead, orbiting like water draining around a whirlpool. The gravitational field is so incredibly intense that it accelerates this material to relativistic speeds, significant fractions of the speed of light. As trillions of tons of gas rub together at these blistering speeds, friction generates immense, unfathomable amounts of heat. Temperatures within the accretion disk soar to millions of degrees, transforming the cold gas into a churning superheated plasma. This plasma glows with brilliant intensity, blasting out high-energy radiation across the electromagnetic spectrum, particularly in the form of X-rays. Ironically, while the black hole itself is completely dark, its accretion disk can shine brighter than an entire galaxy of stars. Slightly further inward, floating just above the point of no return, lies a bizarre optical boundary known as the photon sphere. This is a region of space where gravity is so precise and powerful that it forces photons, massless particles of light, to bend into permanent circular orbits. In standard space, light travels in straight lines. But at the radius of the photon sphere, if you were to stand there and shine a flashlight horizontally, the light would curve completely around the black hole and hit you in the back of the head. You would literally see the back of your own skull. The photon sphere is inherently unstable. Any slight disturbance will cause a photon to either plunge downward into the abyss or escape out into the universe. It represents a boundary of pure optics, creating a ring of light that frames the dark silhouette of the black hole. If the black hole is rotating, which almost all black holes in the universe are, due to the conservation of angular momentum from their parent stars, it possesses a unique, football-shaped region called the ergosphere. This zone sits outside the event horizon and is caused by an extraordinary phenomenon known as frame dragging. As a massive black hole spins, it does not merely spin through space, it literally drags the very fabric of space-time around with it, like a heavy spoon spinning inside a jar of thick molasses. In the ergosphere, the twisting of space-time is so violent that it is physically impossible for any object to remain completely stationary relative to the distant stars. Even if you fired a rocket thruster at maximum capacity in the opposite direction, the sweeping current of space-time would force you to move in the direction of the black hole's rotation. Remarkably, because the ergosphere lies outside the absolute point of no return, it is theoretically possible to enter this region, harness its rotational energy, and slingshot back out into space with more energy than you entered with, a mechanism known as the Penrose process. Directly beneath the ergosphere lies the most famous boundary in astrophysics, the event horizon. This is the true mathematical and physical boundary of the black hole, the absolute point of no return. The event horizon is not a physical surface made of matter. There is no crust, no liquid layer, and no solid barrier. If you were to cross it, you would not feel a sudden impact or a change in local density. It is an informational threshold. At the event horizon, the escape velocity of the black hole exactly equals the speed of light. Because nothing in our universe can travel faster than light, nothing that crosses this threshold can ever escape back out. Not a single particle, not a radio signal, not a memory, and not a secret. The event horizon acts as a one-way mirror in space-time. It completely divorces the interior of the black hole from the rest of the universe, ensuring that whatever happens inside remains permanently shielded from our view. Once an object slips past the event horizon, all paths through space-time are bent inexorably downward toward the absolute center. There are no alternative directions. In the external universe, you can choose to move left, right, up, or down, but you are forced to move forward into the future. Inside the event horizon, space and time swap roles. The inward direction toward the center becomes your future. Trying to escape the center of a black hole is not a matter of lacking powerful rocket engines. It is as structurally impossible as trying to travel backward into yesterday. At the very end of that temporal journey lies the core of the mystery, the singularity. According to Albert Einstein's theory of general relativity, the entire mass of the collapsed star is crushed into a point of zero volume and infinite density. At this mathematical coordinate, the curvature of space-time becomes infinite. The grid lines of the universe break down completely. The laws of classical physics, which we use to understand everything from the movement of planets to the flight of airplanes, are completely shattered. Time, as we understand it, simply stops, and the concepts of space and distance lose all meaning. The singularity is a place where nature divides by zero. Physicists strongly suspect that an infinite singularity does not actually exist in nature, but rather indicates that our current understanding of gravity is incomplete. General relativity treats the universe as smooth and continuous, whereas quantum mechanics treats the universe as discrete and jittery at microscopic scales. To truly describe what happens at the center of a black hole, we require a unified theory of quantum gravity, a framework that merges the physics of the incredibly massive with the physics of the incredibly small. Until that theory is discovered, the singularity remains a blank canvas, a profound blind spot in human science. However, the architecture of a black hole is not merely an inward-facing trap. It also acts as a colossal cosmic engine that flings energy out into the deep trenches of intergalactic space. At the boundaries, where the accretion disk meets the event horizon, immense magnetic fields become twisted and compressed by the rapid rotation of the black hole. These magnetic field lines are squeezed into tight vertical coils, extending above and beyond the spinning axis of the black hole. When superheated plasma from the accretion disk gets caught in these intense magnetic fields, it is not swallowed by the event horizon. Instead, it is channeled away from the boundary and violently accelerated along the rotation axis. This process unleashes the relativistic jets. These are twin, colossal geysers of highly energetic plasma that blast outward from the poles of the black hole in opposite directions. The jets travel across space at near light speeds, covering distances of hundreds of thousands of light years, slicing entirely through galaxies and heating the gas between them. They are among the most energetic and visually spectacular phenomena in the known universe, powered entirely by the invisible gravitational engine at their core. When we look at the complete anatomy of a black hole, we see a fascinating paradox. It is an object defined entirely by its invisibility and its power to consume. Yet its external structures are some of the loudest, brightest, and most disruptive forces in cosmic history. From the blinding light of the accretion disk to the silent geometric trap of the event horizon, and finally to the incomprehensible chaos of the singularity. A black hole is a multi-layered monument to the breaking points of our universe. It challenges our definitions of matter, forces us to rethink the nature of time, and stands as a stark reminder that there are places in the cosmos where our science must begin completely anew. The universe does not build its monsters in only one size. Just as biology ranges from microscopic organisms to colossal blue whales, the cosmos populates its depths with a diverse family of black holes. Astronomers classify these enigmatic objects into 4 distinct categories based primarily on their mass and their cosmic origin. Each class plays a fundamentally different role in the history of the universe, ranging from small hyperactive predators wandering through the star clusters of our own galaxy to ancient incomprehensible titans that hold entire island universes together. The first and most common group is the stellar mass black holes. These are the direct remnants of massive stars that have reached the end of their evolutionary lives. A stellar black hole typically ranges from about 5 times to several dozen times the mass of our Sun. Despite their significant mass, they are astonishingly small in physical size. A stellar black hole with 10 times the mass of our Sun would possess an event horizon spanning roughly 60 kilometers, or about 37 miles across. If you were to place one in the middle of a major city, it would easily fit within the metropolitan limits, yet it would retain a gravitational pull capable of tearing nearby solar systems apart. Stellar mass black holes are scattered abundantly throughout every galaxy. In our Milky Way alone, scientists estimate there could be tens of millions to perhaps 100 million of these cloaked entities. Because they are completely dark, they are notoriously difficult to spot unless they are actively feeding on a companion star or distorting the light of a background object. They represent the natural evolutionary graveyard of the universe's heaviest stars, acting as local traps of extreme gravity hidden among the bright stellar lanes. On the absolute opposite end of the cosmic scale sit the supermassive black holes. These are the true kings of the darkness, possessing masses that range from millions to literally tens of billions of times the mass of our Sun. Unlike their stellar siblings, supermassive black holes do not wander aimlessly through galactic disks. Instead, they anchor the absolute center of almost every large galaxy in existence. The event horizon of a supermassive black hole is so immense that it can swallow entire solar systems whole. For instance, the supermassive black hole at the center of the Milky Way, known as Sagittarius A star, has a mass of roughly 4 million suns. Its event horizon spans about 24 million kilometers across, meaning it could easily fit inside the orbit of Mercury. Even more terrifying are the ultramassive black holes found in distant, giant elliptical galaxies. The Titan, lurking at the heart of the galaxy. Messier 87 has a mass of 6.5 billion suns, throwing a shadow large enough to swallow our entire solar system multiple times over. The origin of these supermassive monsters remains one of the greatest burning questions in modern astrophysics. They could not have formed from a single dying star, as there are no stars large enough to yield such a mass. Instead, scientists believe they began as smaller cosmic seeds in the early universe, rapidly growing over billions of years by continuously consuming vast reservoirs of primordial gas, devouring countless stars, and merging with other black holes during major galactic collisions. For a long time, astronomers faced a deep, troubling paradox in their classification system. They had abundant evidence for stellar mass black holes, and they had undeniable proof of supermassive black holes. But there was a massive, glaring void in the middle, a cosmic missing link known as intermediate mass black holes. These theoretical objects would range from roughly 100 times to 100,000 times the mass of our Sun. Logically, if supermassive black holes grow from smaller ones, the universe must contain mid-sized black holes caught in the transition phase. For decades, finding these intermediate monsters proved to be an extraordinary scientific challenge. They do not sit at the brightly lit centers of major galaxies, nor are they as common as stellar black holes. However, in recent years, advanced astronomical surveys and gravitational wave detectors have finally begun to pull back the curtain on this hidden class. Astronomers have identified strong candidates nested deep within dense, ancient star clusters called globular clusters, as well as in the cores of small dwarf galaxies. Discovering intermediate mass black holes is vital because they provide the crucial evolutionary bridge, proving that black holes can steadily scale up from modest stellar remnants into the galaxy-controlling behemoths that dominate the modern cosmos. The fourth and most speculative category takes us back to the very dawn of time itself: primordial black holes. Unlike the other three classes, primordial black holes do not require the collapse of a star or a long process of cosmic feeding to exist. Instead, they are hypothesized to have formed during the first chaotic fractions of a second following the Big Bang. In that ultra-dense, hyper-energetic nascent universe, space was not perfectly uniform. Some pockets of space would have been slightly denser than others due to random quantum fluctuations. During the early universe, sufficiently overdense regions may have collapsed under their own gravity and formed black holes directly. Because they formed before stars even existed, primordial black holes could theoretically exist in almost any size imaginable. They could be as massive as a mountain, yet compressed down to the physical dimensions of a single subatomic proton. Alternatively, they could be the size of an asteroid or an entire planet. While scientists have not yet definitively confirmed the existence of primordial black holes through direct observation, they remain a highly compelling subject of research. If they do exist, millions of these microscopic or planet-sized ancient traps could be drifting quietly through the dark spaces between the stars. Some astrophysicists have even proposed that a population of planet-mass primordial black holes could account for a portion of the mysterious dark matter that holds galaxies together, or could even explain the anomalous gravitational signatures suspected at the outer fringes of our own solar system. When we survey these four distinct categories, we begin to appreciate how deeply black holes are woven into the structural fabric of our universe. They are not rare anomalies or bizarre accidents of nature. From the subatomic scales of primordial hypotheses to the city-sized stellar remnants, the elusive intermediate stepping stones, and the galaxy-shaping supermassive titans, black holes represent a fundamental, inescapable expression of gravity. They are the universal architects of space and time, demonstrating that no matter how much mass you accumulate, and no matter what epoch of history you examine, gravity always holds the ultimate card, capable of turning any amount of matter into an invisible kingdom of absolute darkness. To truly appreciate how a black hole comes to be, we must examine the violent and dramatic life cycle of the most massive stars in the universe. A star is an engine of pure conflict. Throughout its entire functional life, spanning millions of years, a star is locked in a relentless, brutal tug-of-war against its own mass. On one side of this conflict is gravity, which constantly tries to crush the star's material inward toward a central point. On the other side is the tremendous outward thermal pressure generated by nuclear fusion happening deep within the stellar core. For the vast majority of a star's life, these two opposing forces exist in a state of perfect balance, known as hydrostatic equilibrium. This balance allows stars to shine steadily, illuminating the darkness of space. However, this balance cannot last forever. Stars are powered by finite fuel supplies. A massive star begins its life by fusing hydrogen atoms into helium inside its hyperhot core. When the hydrogen fuel in the core is entirely exhausted, the outward radiation pressure drops, allowing gravity to compress the core further. This compression drives the internal temperature and pressure to astronomical heights, sparking the fusion of helium into carbon and oxygen. This cyclical process continues, with the star burning heavier and heavier elements as the outer layers swell. The star systematically cooks carbon into neon, neon into oxygen, oxygen into silicon, and finally silicon into iron. Each successive stage of fusion yields less energy and transpires at a significantly faster pace, racing toward an inevitable cosmic cliff. When the core of the star transforms into iron, the engine stalls. Iron represents a fatal dead end in nuclear physics. Unlike lighter elements, iron requires more energy to fuse into heavier elements than the fusion reaction itself releases. The reaction becomes strictly endothermic, meaning it drains energy rather than providing it. The moment iron accumulates in the core, the star's outward pressure engine is instantly extinguished. Gravity, which has been waiting patiently for millions of years, suddenly wins the internal tug-of-war completely. With no outward radiation pressure to resist it, the immense mass of the star's outer layers crashes inward at a significant fraction of the speed of light. This catastrophic structural collapse happens with terrifying speed, concluding in just a few fractions of a second. As the outer layers slam into the collapsing core, the extreme densities force electrons and protons together, transforming the core into a solid ball of neutrons. If the star is moderately massive, this sudden compression is halted by a phenomenon known as neutron degeneracy pressure, which is the quantum mechanical resistance of neutrons being packed too tightly together. When the collapsing outer material hits this rigid neutron core, it rebounds violently outward, unleashing a spectacular blinding explosion known as a core collapse supernova. This explosion is so unimaginably energetic that it can briefly outshine an entire galaxy of billions of stars, blasting heavy elements across the cosmos to seed future planetary systems. But what happens to the core left behind? This is where the absolute limits of mass and physics come into play. If the remaining collapsed core is small, it survives as an ultra-dense neutron star. However, there is a strict cosmic speed limit to how much mass a neutron star can support. This limit is known as the Tolman-Oppenheimer-Volkoff limit, which states that a neutron star cannot exceed roughly 2 to 3 times the mass of our Sun. If the dying star was exceptionally massive to begin with, starting its life with 20, 30, or 50 times the mass of the Sun, its collapsed core will easily breach this critical threshold. When the mass of the remaining core exceeds the Tolman-Oppenheimer-Volkoff limit, neutron degeneracy pressure fails. Absolutely no known force in the catalogue of human physics can halt the inward march of gravity. The core begins an infinite, unchecked collapse. It shrinks past the size of an entire planet, past the size of a city, past the size of an atom, and eventually slips beneath its own Schwarzschild radius. The moment the physical dimensions of the matter shrink smaller than this critical mathematical boundary, an event horizon forms around it. The star has officially died, and in its place a stellar mass black hole is born, a permanent scar in the fabric of space-time. Once a black hole is established in the cosmos, it does not sit passively. It interacts dynamically with its local environment, growing larger by consuming any matter that wanders too close to its gravitational domain. The mechanism of how a black hole eats depends heavily on the proximity and configuration of its food source. If a black hole is drifting through a dense interstellar cloud of gas and dust, it pulls the surrounding material inward through gravitational accretion. The gas settles into a rapidly spinning superheated accretion disk, where individual particles frictionally grind against each other, lose orbital energy, and steadily spiral downward across the event horizon. The true horror show begins when an intact, living star ventures too close to a dormant black hole. This event sets off a cataclysmic phenomenon known to astrophysicists as a tidal disruption event. All gravitational fields exhibit tidal forces, meaning that the strength of the gravitational pull changes based on distance. Because a black hole concentrates an immense amount of mass into an extraordinarily compact region of space, its tidal forces are incredibly steep and violent. As an innocent star approaches the black hole, the gravitational pull on the side of the star facing the black hole is significantly stronger than the gravitational pull on the far side of the star. Additionally, the lateral sides of the star are squeezed inward by the converging gravitational lines. When the star crosses a specific boundary, known as the tidal disruption radius, the differential gravitational force exceeds the star's internal self-gravity, the nuclear and gravitational forces holding the star together. The result is immediate and terrifying. The black hole literally rips the star apart, shredding its spherical geometry. The star is stretched and elongated into a long, thin stream of stellar material, in a process poetically referred to as spaghettification. The star ceases to be a star. It becomes a cosmic ribbon of superheated gas millions of miles long. Once the star is disrupted, the dynamics of the ribbon of gas become highly chaotic. Roughly half of the shredded stellar material is flung violently outward into deep space, escaping the black hole's grip entirely at extreme velocities. The remaining half of the star's gas is captured by the black hole, looping back around in highly eccentric orbits. As this returning gas collides with itself, it quickly forms a brand new ultra-bright accretion disk wrapping around the event horizon. The friction and magnetic forces within this freshly formed disk generate temperatures that soar to millions of degrees, producing an immense flare of ultraviolet and X-ray radiation that illuminates the cosmos. For a period of several months to a couple of years, this tidal disruption event shines like a brilliant cosmic beacon, broadcasting the exact location of the otherwise invisible black hole to observatories stationed all across the Earth and in orbit. Eventually, the black hole swallows the remaining gas, returning once more to a state of dark, silent vigilance, having successfully added the mass of a star to its invisible kingdom. Hunting for something that is inherently invisible requires astronomers to become the ultimate cosmic detectives. Because a black hole absorbs all light that crosses its event horizon, scientists cannot look for a black hole directly. Instead, they must observe the profound and soon violent effects these objects exert on their immediate surroundings. Over the past several decades, astrophysics has evolved from a theoretical science into a highly precise observational discipline, utilizing a diverse toolkit of specialized technologies to capture the unmistakable signatures of the universe's most elusive predators. The first breakthrough technique in the history of black hole detection was X-ray astronomy. In the middle of the 20th century, scientists realized that while a black hole itself emits no radiation, the material swirling within its accretion disk is subjected to immense frictional forces and gravitational acceleration. As gas and dust spiral toward the event horizon at a significant fraction of the speed of light, they heat up to millions of degrees, transforming into a superheated plasma. At these extreme temperatures, the plasma glows brightly in the high-energy X-ray spectrum. Because Earth's atmosphere blocks incoming cosmic X-rays to protect life on the surface, astronomers had to launch specialized telescopes into orbit above the atmosphere to detect these signals. In the early 1970s, a satellite observatory named Uhuru detected an exceptionally bright and flickering source of X-rays coming from the constellation Cygnus. This source was catalogued as Cygnus X1. By analysing the optical light of a massive blue supergiant star located in the exact same coordinates, astronomers noticed that the visible star was wobbling violently, locked in a tight orbital dance with an invisible companion object. By measuring the speed of the star's wobble and applying Newton's laws of orbital mechanics, scientists calculated that the invisible companion was roughly 15 times more massive than our Sun. Because this mass far exceeded the physical limit for a stable neutron star, Cygnus X1 became the very first confirmed stellar mass black hole in human history. This discovery proved that we could map the shadows of black holes by measuring the bright X-ray screams of the matter they were actively devouring. While X-ray observations allowed scientists to detect active, feeding black holes, a completely different method was required to observe them when they were colliding in total darkness. This led to the revolutionary field of gravitational wave astronomy. In 1915, Albert Einstein predicted that when massive objects accelerate through space, they should generate ripples in the very fabric of space-time itself, travelling across the universe at the speed of light. These ripples are known as gravitational waves. For a century, these waves remained purely theoretical, because they are unimaginably faint by the time they reach Earth, distorting space by a fraction of the width of an atomic nucleus. To catch these elusive whispers, scientists constructed the Laser Interferometer Gravitational Wave Observatory, or LIGO. LIGO consists of two massive L-shaped facilities located thousands of miles apart in Washington and Louisiana. Each facility features two perpendicular vacuum tunnels stretching 4 kilometers, or 2.5 miles in length. A highly stabilized laser beam is split and sent down both tunnels simultaneously, bouncing off mirrors at the ends to return to a central detector. If a gravitational wave passes through the facility, it momentarily stretches one tunnel while compressing the other, altering the distance the laser beams must travel by an incredibly microscopic distance. On September 14, 2015, LIGO made history by detecting a gravitational wave signal for the very first time, an event catalogued as GW150914. By analysing the frequency and amplitude of the wave, scientists determined that the signal was produced by the violent collision and merger of two stellar mass black holes, one 29 times the mass of the Sun and the other 36 times the mass of the Sun, located over 1 billion light-years away. When they fused into a single black hole, they converted 3 entire solar masses of pure physical matter into raw gravitational wave energy in a fraction of a second, briefly radiating more energy than all the stars in the visible universe combined. Gravitational wave astronomy gave humanity a brand new sense. We could finally hear the invisible collisions of black holes shaking the cosmic fabric. Despite the incredible success of X-ray and gravitational wave detection, the holy grail of astrophysics remained the ability to capture a direct visual image of a black hole's silhouette against the glowing background of its accretion disk. This monumental challenge was undertaken by the Event Horizon Telescope, or EHT, collaboration. To image an object as distant and compact as a supermassive black hole, a telescope would need to possess a resolving power equivalent to standing in New York City and reading the date on a quarter held by someone in Los Angeles. No single telescope on Earth could ever achieve this level of precision. To overcome this physical barrier, the EHT used a technique known as very long baseline interferometry. They link together a global network of highly sensitive radio telescopes scattered all across the planet, including observatories in Hawaii, Chile, Spain, Mexico, and even the geographic South Pole. By synchronizing these individual dishes using atomic clocks and utilizing the rotation of the Earth, the scientists effectively synthesized a single, virtual telescope the size of our entire planet. In April of 2017, this global network turned its collective gaze toward two primary targets: the supermassive black hole at the center of the giant elliptical galaxy Messier 87, and Sagittarius A star, the supermassive black hole anchoring the center of our own Milky Way galaxy. For several days, the telescopes collected petabytes of raw radio data, which were recorded onto high-density hard drives and shipped to central supercomputing facilities in Massachusetts and Germany to be meticulously processed. On April 10, 2019, the EHT collaboration revealed the fruits of their historic labor to the world, the very first direct image of a black hole, specifically the Titan lurking at the heart of Messier 87. The image showed a striking asymmetrical glowing ring of superheated plasma surrounding a circular patch of absolute darkness. This dark region was the shadow of the black hole, the silhouette cast by the event horizon as it trapped all photons attempting to pass by. The bright ring was the superheated gas of the accretion disk, moving toward us on one side at relativistic speeds, which made it appear brighter due to a physics effect known as relativistic beaming. The image looked exactly as Einstein's General Relativity had predicted over a century prior, providing definitive visual proof that these cosmic monsters truly exist in physical reality. 3 years later, in May of 2022, the EHT team achieved an equally monumental feat by publishing the first image of our local supermassive black hole, Sagittarius A star. Because Sagittarius A star is significantly smaller and less massive than the monster in Messier 87, the material orbiting around its event horizon completes a full circuit in just a few minutes, causing the brightness and structure of the disk to shift rapidly during the course of a single observation night. Imaging it was like trying to take a clear photograph of a puppy chasing its tail in a dark room. Through advanced computational algorithms and years of data processing, the scientists successfully filtered out the rapid distortions, revealing a structure remarkably similar to Messier 87, a dark central shadow framed by 3 prominent bright knots of glowing plasma. This image confirmed that our own solar system, along with the hundreds of billions of stars that make up the Milky Way galaxy, orbits around a quiet, dormant, supermassive gravity trap, 4 million times more massive than our Sun. The scientific methods used to observe black holes demonstrate the extraordinary power of human ingenuity. By combining the high-energy eyes of space-based X-ray satellites, the ultra-precise laser corridors of gravitational wave detectors on Earth, and a planet-sized network of radio telescopes working in perfect harmony, humanity has successfully pierced the veil of cosmic darkness. We have proven that the most mysterious and invisible objects in the universe cannot hide from the persistent light of human curiosity. To venture near a black hole is to enter a realm where all human intuition about the nature of space and time is utterly shattered. In our daily lives on Earth, we perceive time as a universal constant, ticking away at the exact same rate for everyone, everywhere. We view space as a static, rigid stage upon which events unfold. But Albert Einstein proved that space and time are fundamentally flexible, woven together into a dynamic 4-dimensional fabric known as space-time. Near the immense gravitational well of a black hole, this fabric is not merely bent, it is twisted, stretched, and warped to such an extreme degree that reality itself undergoes terrifying transformations. The first profound illusion you would encounter as you approached a black hole is gravitational time dilation. According to general relativity, gravity is the curving of space-time caused by mass. The closer you get to a massive object, the stronger the gravitational field becomes, and the slower time passes relative to an observer located far away in flat, undistorted space. If you were to equip an astronaut with a highly precise clock and send them on a trajectory toward the event horizon, while you stayed safely outside aboard a mothership at a distance, a mind-bending temporal paradox would unfold. From your perspective on the mothership, watching the astronaut descend, you would see their clock begin to tick noticeably slower than yours. As they slipped closer and closer to the event horizon, Their movements would appear sluggish, as if they were wading through thick honey. If they tried to wave to you, their hand would move in extreme slow motion. Furthermore, the light waves reflecting off their spacesuit would have to fight against the immense gravitational pull of the black hole to reach your telescope. As those light waves struggled to escape, they would lose energy, causing their wavelengths to stretch out toward the red end of the spectrum in a phenomenon known as gravitational redshift. As a result, you would see the astronaut become increasingly dim and distinctly redder. As they reached the exact threshold of the event horizon, time for them would appear to ground to an absolute halt from your point of view. They would seem to freeze in place, a motionless, highly redshifted, ghostly silhouette stuck on the boundary of the abyss. Eventually, the light would stretch so far that its wavelength would become infinitely long, rendering the astronaut completely invisible to your instruments. You would never actually witness them cross the event horizon. However, the astronaut's own subjective experience would be radically different. From their perspective, as they fell freely toward the black hole, their local clock would continue to tick normally, 1 second per second. They would not feel time slowing down for themselves at all. But if they turned around and looked back out at the universe they were leaving behind, they would witness an astonishing sight. The light arriving from the external universe would be strongly distorted and shifted in frequency. Some distant processes could appear accelerated, but the astronaut would not necessarily witness the entire future history of the cosmos. While the temporal distortions of a black hole are a mesmerizing exercise in theoretical physics, the spatial distortions pose a far more immediate and physically destructive threat to any matter attempting a close approach. This structural nightmare is caused by steep gravitational gradients and is scientifically known as a tidal disruption, or, more evocatively, spaghettification. Tidal forces arise whenever an object experiences a different gravitational pull on different parts of its structure. On Earth, we experience mild tidal forces caused by the Moon. The Moon pulls slightly harder on the oceans facing it than on the solid ground beneath, creating our daily ocean tides. Because the Earth is large and the Moon is far away, the difference in gravitational pull across a human body is entirely imperceptible. But a black hole compresses millions or billions of solar masses into an incredibly compact space, creating a gravitational field that intensifies exponentially over incredibly short distances. If an astronaut were to fall toward a stellar mass black hole feet first, the distance from their feet to their head, roughly 6 feet, becomes a fatal liability. Because gravity increases so sharply as you get closer to the center, the gravitational pull acting on the astronaut's feet would be significantly stronger than the gravitational pull acting on their head. For a typical stellar mass black hole, this differential force would quickly escalate to thousands of times the strength of Earth's gravity. As the astronaut descended, their feet would accelerate downward vastly faster than their upper body. The immediate physical result would be an intense, unbearable stretching along the vertical axis of their body. Simultaneously, because the gravitational lines of force are all converging directly toward the single point of the central singularity, the astronaut's shoulders would be squeezed violently inward along the horizontal axis. As they drew closer to the event horizon, this simultaneous vertical stretching and horizontal squeezing would overpower the structural integrity of their spacesuit, followed quickly by their skin, muscles, and bones. The astronaut would be physically elongated into a long, thin, continuous strand of biological matter. They would literally be transformed into a human noodle, a real-world manifestation of the spaghettification process. The horror of spaghettification does not stop at the macro level of limbs and tissues. As the elongated stream of matter continues its unavoidable plunge toward the core, the tidal forces scale down to the microscopic level. The differential gravity becomes so immensely powerful that it overcomes the electromagnetic forces, the chemical bonds, that hold molecules together. The proteins and DNA within the cells are forcibly ripped apart into individual constituent molecules. Slightly closer to the center, the tidal gradient surpasses the atomic binding energies. The molecules themselves are shattered into individual atoms of carbon, oxygen, nitrogen, and hydrogen. Finally, as the stream approaches the singularity, even the atoms are stripped of their electrons, reducing the matter to a highly elongated, subatomic plasma of naked nuclei and elementary particles. The black hole systematically dismantles the architecture of matter from the outside in, reducing a complex physical entity into an anonymous, uniform thread of fundamental particles stretching toward the mathematical center. Interestingly, the severity of this spaghettification process depends entirely on the size of the black hole you are falling into. If you fall into a relatively small, stellar mass black hole, the event horizon sits very close to the singularity, meaning the gravitational gradient is extremely steep outside the boundary. You would be violently spaghettified into subatomic dust long before you ever crossed the event horizon. However, if you were to fall into a supermassive black hole, such as the titans anchoring the centers of galaxies, the physics flips in a surprising way. Because a supermassive black hole contains millions of times more mass, its Schwarzschild radius is vastly larger, placing the event horizon millions of miles away from the central singularity. Because the boundary is so far out, the gravitational gradient at the event horizon is remarkably gentle. If you fell into a supermassive black hole feet first, the difference in gravity between your feet and your head at the moment you cross the threshold would be completely negligible. You would be able to pass straight through the event horizon entirely intact, feeling absolutely no physical discomfort, completely unaware that you had just crossed the ultimate point of no return. You would have successfully entered the interior of the black hole as a whole human being. Yet this is merely a temporary stay of execution. Once inside the event horizon, your destination is fixed. Space and time warp to the point where the central singularity is no longer a place in space, but an unavoidable moment in your future timeline. As you travel downward through the dark interior, the grid lines of space-time inevitably converge. No matter how massive the black hole is, as you approach the absolute core, the tidal forces will eventually skyrocket to infinity. In the final fractions of a second before you strike the singularity, spaghettification will always claim its prize, stripping your matter down to its very atoms, leaving nothing but an anonymous, stretched whisper of energy to be absorbed by the infinite dark. For many years, astronomers viewed black holes as isolated, purely destructive cosmic anomalies. They were seen as passive traps, silently waiting in the dark corners of space to swallow any unlucky star or gas cloud that crossed their path. They were thought to have no real impact on the broader structure of the universe. However, as advanced space telescopes began to probe the centers of distant galaxies, a profound paradigm shift occurred. Scientists discovered that at the heart of nearly every massive galaxy in the cosmos sits a supermassive black hole. More importantly, they realized that these invisible titans are not detached parasites. Instead, they share a deeply intertwined reciprocal relationship with their host galaxies, co-evolving over billions of years in a spectacular cosmic symbiosis. This realization began when astronomers noticed a striking mathematical correlation known as the M-sigma relation. When scientists measured the mass of supermassive black holes and compared them to the physical properties of the galaxies that housed them, they discovered a tight empirical correlation. Specifically, the mass of a central supermassive black hole is closely correlated with properties of the galactic bulge, including the velocity dispersion of its stars. Typically, the black hole is roughly 1,000th the mass of the galactic bulge. This consistent ratio deeply puzzled astrophysicists. In terms of physical dimensions, a supermassive black hole is a minuscule dot compared to the vast expanses of an entire galaxy. A galactic bulge stretches across tens of thousands of light years, while the event horizon of a central black hole might only span a few light hours. For a black hole to dictate or mirror the scale of an object billions of times larger than itself is equivalent to a single marble controlling the climate and geography of an entire continent on Earth. This proportionality provided clear evidence that the formation of a galaxy and the growth of its central black hole are fundamentally locked together. To understand how this symbiotic evolutionary dance works, we must travel back in time to the early universe, roughly 13 billion years ago. In that ancient epoch, the universe was filled with massive, swirling reservoirs of primordial hydrogen and helium gas. As gravity pulled these gas clouds together, two things happened simultaneously. In the broader regions of the cloud, gas fragmented and collapsed to ignite the very first generations of stars, beginning the construction of the host galaxy. At the exact structural center of the cloud, Where the density was highest and the gravitational potential was deepest, matter pooled at an extreme rate, forming a massive seed black hole. As the newly born galaxy grew by drawing in more surrounding gas from the intergalactic medium, the central black hole fed voraciously on this incoming material. This intense feeding process transformed the dormant black hole into an active galactic nucleus, or a quasar. A quasar is an exceptionally radiant engine powered by a supermassive black hole actively devouring millions of stars worth of gas. As trillions of tons of matter spiral toward the event horizon, the accretion disk becomes so incredibly hot and energetic that it shines with a brilliant intensity, outshining all the combined stars of its host galaxy by a factor of thousands. It is during this hyperactive quasar phase that the black hole begins to exert its immense feedback mechanisms, actively regulating the growth and evolution of the surrounding galaxy. The relationship is a delicate balance of cause and effect, driven by two primary modes of black hole feedback: radiative feedback and kinetic feedback. Radiative feedback occurs when the extreme light and intense radiation blasting outward from the superheated accretion disk strikes the cold gas clouds filling the rest of the galaxy. This intense radiation acts like a colossal invisible broom. It heats the surrounding interstellar gas to millions of degrees, forcing the atoms to move too fast to be bound by gravity. Because stars can only form when cold gas clumps together and collapses under its own weight, heating the gas completely halts all star formation. If the quasar shines brightly enough, the radiation pressure can literally blow the cold gas reservoirs clean out of the galaxy into the empty spaces of intergalactic space. By doing this, the black hole effectively cuts off the food supply for both itself and the growing galaxy, acting as a cosmic thermostat that prevents the galaxy from getting too large too quickly. Kinetic feedback operates through a different, highly mechanical process. As the supermassive black hole spins rapidly at the center of the galaxy, its intense magnetic fields channel superheated plasma away from the event horizon, launching colossal relativistic jets from its poles. These jets blast out across space at near the speed of light velocities, cutting entirely through the galactic disk and extending deep into the surrounding intergalactic clusters. As these jets plow into the hot gas surrounding the galaxy, they create immense shockwaves and massive bubbles of energy. This mechanical disruption injects vast amounts of heat into the galactic atmosphere, preventing the surrounding gas from cooling down and falling back into the galaxy. Without a steady supply of cool, falling gas, the galaxy cannot produce new generations of stars, and the central black hole is starved of fresh material to consume. This feedback loop represents a stunning example of cosmic self-regulation. When a galaxy has an abundance of cold gas, it feeds both star formation and the central black hole. As the black hole consumes this matter, it ignites into a brilliant quasar, launching powerful radiation and massive jets that heat and blow away the remaining cold gas. Once the cold gas is gone, star formation stops and the black hole starves, turning off its intense radiation and jets. Over millions of years, the galaxy cools down once more, allowing gas to pool at the center again, restarting the cycle. Through this continuous dynamic dialogue, the tiny black hole actively controls the demographic history of the entire galaxy, determining exactly how many stars can be born and when the galaxy must enter a period of structural dormancy. The profound impact of this relationship becomes even more dramatic during major galactic collisions. When two large galaxies are drawn together by gravity over billions of years, they undergo a violent merger process. As the disks of the two galaxies smash into each other, the immense gravitational forces disrupt the orderly orbits of gas and stars. Vast reservoirs of gas are violently funneled toward the center of the newly merging system. This sudden, massive influx of gas triggers a spectacular burst of new star formation, known as a starburst galaxy. Simultaneously, this incoming tide of matter reaches the central regions, where the supermassive black holes of both original galaxies are steadily sinking toward each other. The dual black holes feast on the newly available gas, igniting twin quasars that blast immense amounts of energy into the chaotic, merging system. Eventually, the two supermassive black holes spiral close enough to lock into a gravitational embrace, swirling around one another before colliding and merging into a single, even more massive titan. The energy released by this black hole merger shakes the fabric of space-time across the entire universe. Once the merger is complete, the single, giant, supermassive black hole unleashes a final, devastating wave of feedback. The combined energy of its active phase heats and expels any remaining gas from the newly formed merged galaxy. With its gas completely cleared out, the galaxy loses its ability to form new stars entirely. The vibrant, blue, star-forming spiral galaxies are transformed into a single, massive, dull red elliptical galaxy, a cosmic graveyard populated entirely by aging, long-lived stars. When we look at the modern universe, we see the definitive results of this long, symbiotic evolution. Black holes are not random vandals tearing up the cosmic landscape. They are the supreme architects of galactic structure. Without the regulatory feedback of supermassive black holes, galaxies would have consumed all their gas in rapid, uncontrolled bursts of star formation early in cosmic history, leaving a universe of bloated, unstable stellar systems. By acting as a powerful brake on star formation, black holes ensure that galaxies grow in an orderly, balanced fashion over billions of years. The invisible monsters in the dark are the very engines that sculpted the beautiful, starry structures of the universe we see today. For nearly a century, modern physics has operated under a profound and troubling identity crisis. Our understanding of the physical universe is split cleanly into two exceptionally successful, yet completely incompatible theoretical frameworks. To explain the cosmos on a grand scale, the movement of planets, the orbits of galaxies, and the geometric warping of space and time, we rely on Albert Einstein's theory of general relativity. General relativity treats the universe as a smooth, continuous, and completely deterministic fabric. Conversely, to explain the universe on the microscopic scale, the subatomic world of electrons, protons, and quarks, we rely on quantum mechanics. Quantum mechanics describes a universe that is fundamentally grainy, chaotic, probabilistic, and governed by discrete packets of energy. For the vast majority of scientific applications, these two theories never interact. Astronomers do not need to worry about quantum uncertainty when calculating the orbit of Jupiter, and particle physicists do not need to account for gravitational space-time curvature when smashing electrons together inside a laboratory accelerator. However, there is one place in the universe where these two isolated worlds are forced to collide: the black hole. A black hole represents the ultimate theoretical paradox, compressing a colossal, astronomical mass down into an unimaginably tiny, subatomic volume. To describe its physics, you must simultaneously utilize the laws of the incredibly massive and the laws of the incredibly small. When physicists attempt to mathematically merge the smooth equations of general relativity with the jittery equations of quantum mechanics at the event horizon, the math breaks down completely, yielding nonsensical answers of infinite probabilities and structural contradictions. A black hole is a theoretical battlefield where our two greatest descriptions of reality go to war. The first major breakthrough in resolving this conflict came in 1974, courtesy of the brilliant British theoretical physicist Stephen Hawking. Before Hawking's work, physicists believed that black holes were completely inert, frozen traps. If nothing could escape the event horizon, then a black hole could never emit any form of light, heat, or particle. It was a one-way street that remained dark for all eternity. Hawking challenged this view by applying quantum field theory to the empty space directly surrounding the event horizon. According to quantum mechanics, empty space, the vacuum of the cosmos, is not completely empty or inert. Instead, it is a churning, hyperactive sea of quantum activity, governed by the Heisenberg uncertainty principle. This principle allows energy to be briefly borrowed from the universe to create pairs of virtual particles. These pairs consist of a particle and its corresponding antiparticle, which pop into existence simultaneously out of the vacuum. Typically, these virtual particles find each other almost instantly, annihilating one another and returning the borrowed energy back to the quantum vacuum in a fraction of a millisecond. This continuous cycle occurs everywhere throughout the universe, all the time, completely undetected. Hawking calculated what would happen if a pair of these virtual particles popped into existence precisely at the absolute boundary of the event horizon. He discovered that occasionally, one of the virtual particles will cross the point of no return, falling inside the event horizon, while its partner particle remains stranded just outside in the free universe. Because the particle that fell inside is trapped forever by gravity, the pair can no longer meet to annihilate each other. The stranded particle outside is suddenly orphaned. It is transformed from a fleeting virtual particle into a real, physical particle with positive energy. To an outside observer looking at the black hole from a distance, this orphaned particle appears to be radiated away from the boundary as a faint glimmer of heat. This phenomenon is now universally known as Hawking radiation. But where did the energy come from to turn a virtual particle into a real one? The universe requires a strict balance of mass and energy. Because the particle that escaped has positive energy, its partner that fell into the event horizon must possess negative energy relative to the outside world. When the negative energy particle strikes the singularity at the center, it effectively subtracts mass from the black hole. Therefore, by emitting Hawking radiation, a black hole does not just sit there, it actively loses mass and energy over time. Hawking radiation revealed a shocking cosmic truth. Black holes are not completely black, and they are not eternal. They are slowly evaporating, leaking energy out into the cold spaces of the universe. The rate of this quantum evaporation depends entirely on the size of the black hole. A massive black hole possesses a gentle curvature at its horizon, meaning its quantum vacuum is less disrupted and it evaporates at an exceptionally slow pace. A supermassive black hole would take longer than the current age of the universe to radiate away a fraction of its mass. However, as a black hole loses mass, its event horizon shrinks, the gravitational gradient becomes steeper, and the rate of Hawking radiation accelerates dramatically. As the black hole approaches the final stage of evaporation, the radiation may intensify dramatically. The precise nature of the final stage remains uncertain, because it depends on quantum gravity physics that is not yet fully understood. While Hawking radiation provided a brilliant bridge between gravity and quantum mechanics, it simultaneously unleashed a devastating intellectual crisis known as the black hole information paradox. This paradox threatens to tear down the entire foundational structure of modern physics. In quantum mechanics, there is a fundamental law known as quantum unitarity, which states that information about the physical state of a system must always be preserved. Information, in this scientific context, does not mean written words or computer data. It means the precise arrangement, spin, charge, and quantum states of the fundamental particles that make up an object. If you burn a book, quantum mechanics states that the information within that book is not truly lost to the universe. If you were to meticulously collect every single particle of ash, every photon of light emitted by the flame, and every molecule of smoke, you could theoretically use the laws of physics to reverse the process and perfectly reconstruct the book. The past is always mathematically encoded in the present. The introduction of Hawking radiation completely shatters this foundational law. Imagine taking that same book and throwing it straight into a black hole. Once the book crosses the event horizon, its physical matter is crushed into the central singularity, adding its mass to the overall black hole. According to general relativity, the only properties a black hole retains from the things it swallows are mass, electric charge, and angular momentum. This is known as the no-hair theorem. The black hole does not care whether you threw in a book, a grand piano, or a block of lead. It only registers the total mass. If the black hole then proceeds to evaporate via Hawking radiation over trillions of years, the radiation it emits is completely random and thermal. The outgoing photons appear to carry no recoverable information about the specific things that were once swallowed to create that mass. When the black hole finally explodes and vanishes entirely from existence, the physical information that was inside the book appears to be completely erased from the universe forever. This is the core of the paradox. If the information is truly destroyed, then quantum mechanics is fundamentally wrong, and the law of conservation of information is a lie. If information can vanish, then the past cannot be reconstructed from the present, and the core determinism of physics is broken. Conversely, if general relativity and Hawking's original calculations are correct, the information must be destroyed, because the interior of the black hole is permanently cut off from the outside world. Physicists were left with an impossible choice. Either Albert Einstein's description of space-time geometry is incorrect at the horizon, or the foundational laws of quantum mechanics are invalid. For the past several decades, The world's greatest theoretical minds have locked themselves in intense debate to resolve this existential crisis. One of the most popular proposed solutions is the holographic principle, championed by physicists like Leonard Susskind and Gerard 't Hooft. The holographic principle suggests that whenever an object falls toward a black hole, the information about its subatomic state is not actually carried inside the horizon. Instead, as the matter crosses the boundary, its quantum information is stripped away and flatly encoded onto the two-dimensional surface of the event horizon itself, scrambled like a complex hologram. When the black hole evaporates, the outgoing Hawking radiation interacts with this encoded surface, carrying the scrambled information back out into the universe bit by bit. From this perspective, the interior of the black hole might be an illusion, and all three-dimensional reality could be a projection of information stored on a distant two-dimensional boundary. Other theorists propose that the information remains trapped at the very end of the evaporation process, leaving behind a stable, microscopic remnant the size of the Planck length that holds all the accumulated information of everything the black hole ever swallowed. Others suggest the information escapes through hidden quantum wormholes, linking the interior to the outside world. The battle over the black hole information paradox remains entirely unresolved, standing as the ultimate frontier in modern physics. It demonstrates that black holes are not merely interesting objects for astronomers to look at through radio telescopes. They are the supreme testing grounds for our understanding of reality. By forcing general relativity and quantum mechanics into a direct, violent confrontation, the black hole challenges us to discover a deeper, more unified law of nature, an elusive theory of everything that can finally explain how space, time, matter, and information truly behave at the absolute limits of existence. When we push the mathematical foundations of general relativity to their absolute limits, we leave behind the world of direct observation and step squarely into the realm of theoretical speculation. Black holes are no longer the final word in cosmic weirdness. Instead, the very same equations that predict the existence of these gravitational traps also hint at a collection of even more bizarre mirror image structures and cosmic gateways lurking at the fringes of scientific understanding. These hypotheses represent the true borderlands of modern physics, where the geometry of space and time becomes so deeply distorted that it opens the door to science fiction concepts like time travel, alternate dimensions, and the birth of entirely new universes. The first and most direct mathematical mirror to a black hole is a hypothetical object known as a white hole. To understand where a white hole comes from, we have to look at the mathematics of Karl Schwarzschild's solutions to Albert Einstein's field equations. Einstein's equations are fundamentally time-symmetric, meaning they work perfectly whether time flows forward into the future or backward into the past. If a black hole represents an astrophysical object where matter can only enter but can never escape, the time-reversed solution of the exact same math yields an object where matter can only escape but can never enter. This is a white hole. Geometrically, a white hole reverses the rules of the event horizon. Instead of an absolute gravitational pit, a white hole possesses a boundary that violently expels matter and radiation into the cosmos at relativistic speeds, acting as an intense, blinding cosmic fountain. No matter how hard you try, it is physically impossible to cross the threshold of a white hole from the outside. The outward pressure and the geometry of space-time itself will always push you away. While mathematicians can easily sketch a white hole on a chalkboard, finding one in the real universe is a completely different challenge. Unlike black holes, which form naturally through the gravitational collapse of massive dying stars, there is no known physical mechanism in astrophysics that can naturally build a white hole. Furthermore, white holes appear to violate the second law of thermodynamics, as they would spontaneously decrease entropy by generating highly organized streams of matter out of a single point. Because of these profound physical barriers, most contemporary physicists view white holes as mathematical illusions, a quirk of the equations that does not exist in nature. However, a few radical theorists have suggested that white holes might not be isolated objects, but rather the highly explosive final stage of an evaporating black hole, or perhaps even the true identity of the Big Bang itself, an intense, sudden unfolding of space and matter emerging from a singularity. If white holes do exist anywhere in the cosmos, they immediately introduce the possibility of an even more spectacular structure, the Einstein-Rosen bridge. Commonly referred to in popular culture as a wormhole. In 1935, Albert Einstein and his colleague Nathan Rosen examined the geometry of the intense space-time curvature near a singularity. They discovered that if you mathematically connect the throat of a black hole to the throat of a white hole, you create a continuous, highly distorted tunnel through the fabric of the universe. An Einstein-Rosen bridge effectively acts as a geographic shortcut through the fourth dimension. Imagine drawing two distant dots on a flat sheet of paper, representing two solar systems separated by billions of light-years of empty space. To travel from one dot to the other along the surface of the paper would take billions of years, even at the speed of light. But if you fold the paper in half so that the two dots sit directly on top of each other, and then poke a pencil straight through the layers, you create a direct tunnel. By travelling through the tunnel, an explorer could span cosmological distances in a fraction of a second, effectively bypassing the universal speed limit of light. However, actually utilising an Einstein-Rosen bridge for interstellar travel presents immense, almost insurmountable physics engineering hurdles. The standard mathematical wormholes derived from general relativity are notoriously unstable. The moment any amount of physical matter or light attempts to enter the throat of the tunnel, the gravitational disruption causes the wormhole to instantly pinch shut and collapse back into a pair of isolated singularities, crushing the traveller inside. To keep a wormhole propped open, a civilization would need to line the throat of the tunnel with a highly exotic form of matter that possesses negative mass and negative energy density. This exotic matter would generate a repulsive gravitational force, counteracting the immense inward pull of the singularity and keeping the corridor stable. While quantum mechanics allows for the existence of tiny pockets of negative energy via phenomena like the Casimir effect, whether enough exotic matter can ever be gathered to stabilize a macroscopic wormhole remains a profound and deeply debated question at the edge of science. If wormholes are real, they do not just alter our understanding of space, they fundamentally shatter our linear perception of time. Because space and time are inextricably linked in a single fabric, if you were to accelerate one mouth of a stable wormhole to near the speed of light velocities, while keeping the other mouth stationary on Earth, time dilation would occur. The moving mouth would age significantly slower than the stationary mouth. An explorer could then step into the earthbound mouth, travel through the stabilized Einstein-Rosen bridge, and exit the moving mouth at a point in the past. This configuration transforms the wormhole into a functional time machine. The existence of such a device creates profound causal paradoxes, such as the grandfather paradox, where a traveller could theoretically go back in time and alter history in a way that prevents their own birth. To resolve these contradictions, physicists like Stephen Hawking propose the chronology protection conjecture, suggesting that the laws of quantum mechanics will always conspire to trigger a massive buildup of energy that destroys any wormhole the moment it attempts to form a closed, time-like curve. The most sweeping and breathtaking hypothesis born from the study of black holes takes us beyond the borders of our own cosmic bubble entirely, into the theory of cosmological natural selection, or the fecund universes hypothesis, pioneered by theoretical physicist Lee Smolin. This model suggests that the singularity at the centre of a black hole is not a dead end where physics stops, but rather a cosmic seed. When a massive star collapses into a singularity, the density and gravitational curvature reach a critical point where the local fabric of space-time undergoes a profound phase transition. Instead of crushing matter into a mathematical zero, the extreme energy causes space to rebound, inflating outward in an entirely new direction that is completely inaccessible from our universe. This internal expansion is structurally identical to a Big Bang. In other words, every single black hole that forms in our universe gives birth to an entirely new, independent baby universe inside its singularity. This hypothesis leads directly to a grand vision of a cosmological multiverse, organized through a process remarkably similar to biological evolution. According to Smolin's theory, when a baby universe buds off from a parent universe through a black hole singularity, the fundamental constants of physics, such as the strength of gravity, the mass of the electron, and the speed of light, are passed down to the new universe, but with slight, random quantum variations. If a baby universe inherits a combination of physical laws that allows it to easily form massive stars, those stars will eventually die and create an abundance of new black holes. Each of those new black holes will, in turn, give birth to another generation of baby universes. Over vast spans of cosmic time, the multiverse becomes heavily populated by universes whose physical laws are highly optimized for the production of black holes. Remarkably, when we look at our own universe, we find ourselves living in a cosmos that seems extraordinarily fine-tuned to produce black holes. If the strong nuclear force were just a fraction different, stars would not ignite correctly, and the gravitational collapse required to form event horizons would never occur. The fecund universes hypothesis provides an elegant, non-anthropic explanation for this fine-tuning. Our universe looks the way it does because it is the highly successful descendant of a long line of ancestral universes, tracking back through a vast, interlinked genealogical tree of black hole singularities. These ideas remind us that our current map of the cosmos is likely only a single page in a much larger, infinitely more complex book. By transforming the black hole from a simple, destructive vacuum into a potential gateway to white holes, a shortcut through time-traveling wormholes, or the literal birthplace of entire new universes, modern theoretical physics challenges us to see the absolute darkness not as an ending, but as the ultimate beginning. To see the ultimate destiny of black holes, we must look beyond our current epoch and travel into the deepest, unimaginably distant future of the cosmos. Right now, we live in the stelliferous era, a vibrant, youthful age of the universe where galaxies are packed with billions of blazing stars. New solar systems are continuously forming, and energy flows abundantly through space. But this starry golden age is a fleeting moment in the grand timeline of eternity. Over the next few 100 billion years, the universe will steadily consume its remaining reservoirs of hydrogen gas. One by one, the stars will burn through their nuclear fuel, dimming from vibrant blue giants into long-lived red dwarfs, before eventually going dark completely, leaving behind a cold cosmos populated by stellar remnants. By the time the universe reaches roughly 100 trillion years into the future, all conventional star formation will cease forever. The cosmos will enter the degenerate era. During this long, gloomy twilight, the universe will be dominated by white dwarfs, neutron stars and brown dwarfs, dead stellar husks, slowly cooling down toward absolute zero. Yet, even these solid remnants cannot endure forever. According to many mainstream grand unified theories of particle physics, the fundamental building blocks of standard matter are unstable over immense timescales. Protons, the subatomic particles that form the nuclei of every atom in the universe, are hypothesized to decay. Over a staggering period spanning up to 10 raised to the power of 40 years, all white dwarfs and neutron stars will systematically dissolve, their constituent atoms breaking apart and evaporating into a faint haze of elementary particles. When the last solid matter dissolves, the universe will cross a profound threshold and enter the black hole era. In this unimaginably distant epoch, black holes will be the sole remaining macroscopic structures in existence. Every stellar mass black hole created by the collapse of ancient stars, every intermediate stepping stone, and every supermassive titan that once anchored the centers of majestic galaxies will inherit the empty, expanding ruins of the cosmos. The universe will become a vast, featureless graveyard of absolute darkness, spanning light years of void, where the only active sources of gravitational influence are these invisible monsters. During the black hole era, these objects will rule the cosmos, but they will be entirely trapped in a slow, agonizing process of self-destruction. As we established through quantum mechanics, black holes are not perfectly stable. They leak energy into the vacuum via Hawking radiation. Because the ambient temperature of the expanding universe will have fallen extremely close to absolute zero, far colder than the internal temperature of even the largest black holes, the cosmic balance will shift completely. Black holes will no longer absorb any background radiation from space. Instead, they will exclusively emit an incredibly faint, continuous stream of low-energy photons and elementary particles. For an unfathomable duration of time, this quiet quantum evaporation will be the only event taking place in the entire cosmos. A stellar mass black hole will take roughly 10 raised to the power of 67 years to fully evaporate. The supermassive monsters, possessing the mass of billions of suns, will endure much longer, slowly shedding their mass over an agonizing span of 10 raised to the power of 100 years. human minds cannot truly comprehend a number of this scale. It is a timeline where the entire multi-billion-year history of our current starry universe is less than a microscopic fraction of a single second. As a black hole sheds its mass over these eons, its event horizon gradually contracts. As the physical radius of the boundary shrinks, the local curvature of space-time at the threshold becomes increasingly sharp and violent, causing the rate of Hawking radiation to accelerate rapidly. An object that spent trillions of years quietly leaking faint photons will suddenly begin to glow with intense thermal heat. In its final centuries of existence, a dying black hole will radiate energy with the brightness of a star. In its final seconds, the evaporation process reaches a runaway crescendo. Depending on the still unknown physics of the final evaporation stage, the remaining mass may be released in a brief burst of high-energy particles and gamma rays before the black hole disappears. One by one, across the cold, dark expanses of the expanding void, the universe's ultimate monsters will detonate and vanish into nothingness. When the very last supermassive black hole completes its final explosive evaporation, the black hole era will draw to a definitive close, and the universe will enter its final structural phase, the dark era. In this eternal aftermath, the universe is completely devoid of matter, gravity traps, and structural complexity. The cosmos will expand indefinitely, cooled to temperatures extremely close to absolute zero. All that remains of the once vibrant universe is a dilute, anonymous sea of isolated electrons, positrons, and ultra-low energy photons, wandering aimlessly through an infinite, dark vacuum. The spectacular story of space and time, which began with the blazing light of the Big Bang and was sculpted for eons by the gravity of black holes, dissolves into a silent, timeless ocean of cold radiation. The cosmic monsters will have completed their work, leaving behind a universe wrapped in perfect, everlasting peace. Our journey into the deepest trenches of cosmic darkness brings us to a profound realization. Black holes are not the purely destructive monsters they initially appear to be. While they possess a terrifying power to consume matter, produce extreme gravitational time dilation, and tear stars apart through tidal forces, they are simultaneously the supreme architects of our universe. Without the influence of supermassive black holes, the evolution of many galaxies and their central regions could have unfolded very differently. They are the ultimate engines of balance, regulating the growth of galaxies through powerful energetic feedback, ensuring that the cosmos evolved with structural harmony over billions of years. By pushing the absolute limits of Einstein's general relativity and the chaotic rules of quantum mechanics, black holes stand as the ultimate laboratories for human science, challenging us to rewrite our understanding of reality, information, and time itself. They remind us that the universe is far stranger, more beautiful, and more deeply interconnected than our daily lives on Earth could ever suggest. As we watch these invisible titans shape the past, dominate the modern night sky, and carry the distant future of the cosmos toward its final, quiet destiny, we are reminded that the dark spaces of the universe hold the answers to our greatest scientific questions. Thank you for venturing out to the absolute edge of existence with us today. Your curiosity and passion for discovery are what drive this channel forward. Keep looking up at the stars, keep questioning the unknown, and never stop exploring the deep mysteries of this beautiful cosmos. Until our next journey through space and time, stay curious, stay safe, and goodbye.